Towards the beginning of the semester, we learned about the periodic table and how it was set up. We're going to take a little bit deeper look at the periodic table and determine some of its properties and why these trends are seen. So if you remember, we have the periodic table. It's divided into groups and periods. Each period, remember, represents an energy level. So we have energy level 1, 2, 3, 4, 5, 6, and 7. We know that we have sublevels. We know that our S, P, D, and F. So this would be the S, this is the D, this is the P, and this is the F sublevel. We know we have groups, and within the groups, 1 through 18, we have specific trends. Elements in the same group have similar properties. They have the same number of valence electrons. These valence electrons are responsible for those properties and how the elements interact and react with each other. If elements are grouped in order of their atomic numbers, it's going to be found that nearly the same properties recur periodically through the entire series. And we can see this. Everything in group 1 has similar properties. Everything in group 2 has similar properties. When we refer to size of an atom, we usually say the atomic radius. Now, the atomic radius is, if we look, remember the atom is spherical. You have your nucleus in the center, and the atomic radius is measured from the nucleus to the outermost energy level, where you have your valence electrons. So you can have various energy levels. This one, of course, has 1, 2, 3. The radius is always at the outermost energy level. We have experimentally found that there are trends or periodicities to the atomic radius of the main group elements. The main group elements do not include the lanthanide and actinide series or the transition elements. They're just groups 1, 2, 13, 14, 15, and 16, 17, and 18. Now, if we look at this, since we have experimentally measured each of the atomic radii of the elements, if we look, we know that here, lithium, sodium, potassium, rubidium, cesium, and francium are all in the same group. So what do we notice if we go ahead and say, well, we're going to graph atomic radius by atomic number? What do we notice happens with the atomic radius from lithium to sodium, from sodium to potassium, from potassium to rubidium, from rubidium to cesium? They all increase. So as we go down the periodic table, the radius increases. Now let's look as we go across the periodic table. Lithium and fluorine are on the same period. They're on the same row. So if we go across, what happens if we graphed every single element in that row? What happens to the radius? It goes from 150 to about 75. Okay, let's look at the next row. If we look at sodium, that's about 175. And it goes to about 75. So here. Potassium is about 225. It goes to about 100. So we know that as we go across, it's actually decreasing. As we go across a period. But we don't know why yet. So let's look and see what's happening so that we can determine why we see this group. It's not enough to know the trend, but we should understand why. So if we look at period 3, we're staying in the period where all of these elements are in period 3 here. You have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. We can see that the atomic radius is decreasing within that same period. Well, what happens to the energy level as we go across the period? It's actually staying the same. The energy level is remaining constant because all of these, remember, if we have our periodic table here, we have our first period, our second period, our third period. Each row represents an energy level. We're right here with sodium. This one would be argon right here. So we're in this energy level. The energy level is remaining constant. But what happens to the atomic number or the number of protons? Because remember, the atomic number tells us the number of protons. So what happens to the atomic number as we move across the period? So this was 11, then we have 12, we have 13, 14, 15, 16, 17, and 18. The atomic number is increasing. So that means we have the number of protons that are increasing. If we have increasing number of protons, remember the atomic number tells us the number of protons, and in a neutral atom, which all of these are, it tells us the number of electrons. So if the number of protons is increasing as we go across the periodic table, the number of electrons is also increasing. What happens to magnetic forces? Because electrons are negative, protons are positive. Think about your magnets. They have a positive and negative side too. So if we have, let's say, one magnet, a positive and a negative, how strongly are those attracted to each other compared to something that might have 6 magnets? If you group 6 magnets together, is it how is that attractive force compared to just 2 magnets? Are these going to be held more tightly together than just these two? Yeah, there's more charge, there's more force here. So it's going to have that stronger attractive force to pull it together, more so than just this positive and negative. There's still an attractive force here, but it's not as strong as the multiple magnets. So take that and think of it as protons and electrons. The more protons and electrons you have, the greater the attractive force. So that's why it's a smaller radius as you go across the periodic table, because the attractive force increases, pulling those protons and electrons together. So the electrons are pulled closer to the nucleus. and therefore held more tightly. And that's why the radius gets smaller as you go across the periodic table. Now let's look at the group 1 elements. What's happening in the periodic table as you go down a group? So say we have lithium, we have sodium, we have potassium, we have rubidium, we have cesium here. So let's look at that. Lithium is in group 2, or sorry, is in period 2. Sodium is in period 3, 4, 5, 6. So we know that each energy level corresponds to the period number. So lithium is in energy level 2. Sodium is in energy level 3. Potassium is in energy level 4. Rubidium is in energy level 5. Cesium is in energy level 6. So as we go down a group, we are increasing energy levels. So if we're increasing energy levels, what happens to the size? Because here, let's look at this. This is our nucleus. We have 1 energy level. We have 2 energy levels. We have 3 energy levels. We have 4 energy levels. What's happening to our size as we add more energy levels? Right. So the size is increasing. We're adding more energy levels, so those electrons are going to be farther and farther away from the nucleus because we have more energy levels. So that's why as we go down the periodic table, the atomic radius increases. So let's do a recap of all the trends. So within a given group of the periodic table, atomic radius increase with increasing atomic number. And that's because the outer electrons are in levels of increasing energy. As you add more energy levels, you're going to have greater distances from the nucleus. Now within the period, so across the periodic table, the outer electrons are in the same energy level, but they're going to have an increasing force of attraction from an increasingly positive charged nucleus, and that causes, quote, shrinking in the average radius of the outer electrons, and the average distance of the outer electrons, that's distance. And then remember, because you have more of that attractive force, so that distance is decreased. It's being held more tightly. So let's look at the radius of ions. This is a sodium ion, and it has a radius of 186 picometers. But when it becomes an ion, it has a radius of 99 picometers. Magnesium goes from 160 picometers to 65 picometers. What happens for an atom that's metal to become an ion? What happens? Remember, we had our sodium with our ion, or with our atom here, and then our chlorine, if we draw here. And there was a transfer of electrons. So then sodium became positive, and then chlorine had its full valence, and both were stable. So remember, in order to become a positive ion, you lose an electron or more. In the case of magnesium, it lost two. So you lose electrons to become a positive ion. So how does the size of a positive ion compare with the atom from which it was made? So the positive ions are smaller than the neutral atoms. And let's think about this. Why? Why would the positive ion be smaller than its neutral atom? Remember, we have our atom here. What's happening? Well, if you lose these electrons, you've lost any attractive forces there. So now, say we have 5 positive charges, but only 3 minus charges. So these electrons are going to be even more strongly attracted to the positive charges. You've lost this energy level, so it's already smaller, but now you have that imbalance of charges as well. So that's why it's so much smaller, is mainly due to this imbalance of charges. You have more protons than you do electrons. And so therefore those electrons, they're not balancing out those positive charges anymore. They're just strongly attracted to them. And it's going to get even closer to those positive charges. Now, how can an atom become a negative ion? We've already talked about this as well. We saw that chlorine took one of sodium's electrons. And so it takes another electron. Now, if it takes another electron, see that you're going to have an imbalance of negatives to positive. So you're going to have more negatives, more negative charges than positive charges. This will result in a loosely held atom. The electrons aren't going to be held as tightly to the nucleus because there are more electrons. That charge balance has been lost. So the protons in the nucleus are trying to hold more electrons than what it usually is. So that slight imbalance is going to cause those electrons to be more loosely held. If they're more loosely held, they're going to have more space. So the size of an anion is larger than the neutral atom because of that atom or that ion having more electrons than it does protons. Now, how does the size of an atom change when it becomes an ion? This is just a recap. The atom, of course, we know can either get smaller if it loses an electron, or it can get bigger if it gains. If it becomes smaller from losing electrons, this is because there are more protons in the nucleus, which hold the electrons more tightly. Atoms become larger as they gain electrons because you have more electrons than protons. And so again, you have a charge imbalance. The electrons are held less tightly, resulting in a larger size. Now the ionic size increases as you go down a group. Positive ion size decrease as you go across a period. The negative ion size decrease as you go across a period. Those are just some recap things. Let's do some practice. Which of the following ions is smaller than its neutral atom? Would it be sodium, chlorine, or chloride, oxide, or fluoride? Which one will get smaller? I want you to try to answer these on your own and then come back and review them with us. So which of the following ions is smaller than its neutral atom? The answer would be sodium. Sodium loses an electron to become sodium ion, and there will be one less energy level, and you will have an imbalance of electrons to protons. So you'll have more protons than you have electrons, so those electrons are going to be held more tightly to the nucleus. Now, why is a chloride ion larger than a chlorine atom? What happens? It's C. It gains an electron, which increases the repulsion between those electrons. Which of the following ions is the largest in size? To do this, we'll need to look at the periodic table to kind of see where things are. And remember this. Positive ion size decreases as you go across the periodic table, and negative ion size decreases as you go across the periodic table, but ionic size increases as you go down a group. So remembering those, and then looking at the periodic table, we have magnesium, sodium, aluminum, and largest in size. We come back here, we have sodium, magnesium, aluminum, and oxygen. We know that the size of ions decreases as we go across the periodic table. Now, oxygen is not in the same period. We also know that as we go down the periodic table, the size of ions decreases. So oxygen, since it's not in the same row, would be the correct answer. Let me know if you have questions, and I'm happy to help.